I'm audible? Hello? 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 వినపడుతుందండి? I'm audible అండి రవి అండ్ శ్రీలత. హలో, I'm audible అండి మిస్టర్ రవి.
సార్ ఓకే సార్, వాయిస్ వినబడుతుంది సార్. గుడ్ మార్నింగ్ సార్, శ్రీలత సార్.
హలో
హలో సార్, వాయిస్ వినబడుతుంది సార్.
హలో
హలో, మై నేమ్ ఈస్ శ్రీలత సార్. హలో హలో, గుడ్ మార్నింగ్ సార్.
I'm audible.
హలో,
శ్రీలత, I'm audible.
వాయిస్ వినబడుతుంది సార్.
ధనలక్ష్మి, I'm audible. Hello, hello. Yes, I'm audible.
హలో,
I'm starting today. Starting with the online classes, complex analysis. So today we are discussing about complex analysis. Now, what is the complex analysis? So in this chapter with the complex analysis, we shall discuss the constructions of the system of the numbers containing the familiar real numbers and also permitting the solution of equation that is x square plus 1 is equal to 0. I'm also sharing the screen here.
Good morning, sir.
Voice
Hello.
Voice వినబడుతుందా?
వినబడుతుంది సార్.
The screen is visible. Dhanlakshmi.
Sir. Good morning, sir. Good morning, Anna. Good morning. Good morning, sir.
So today So today we are discussing. Today we are discussing about I am audible. వినబడుతుందండి?
క్లాస్ అది ఆన్లైన్ క్లాస్ అది.
ధనలక్ష్మి, శ్రీలత, వేదశ్రీ. I am audible, అమ్మా?
సార్
ధనలక్ష్మి
సార్
వినబడుతుందా?
సార్ మీది వినబడుతుంది సార్. కొంచెం గట్టిగా చెప్పండి.
హలో
గట్టిగా చెప్పండి సార్ కొంచెం.
హలో
హలో సార్.
హలో హలో
హలో సార్.
హలో
హలో సార్. హలో సార్ వినపడట్లేదు.
about the
Good morning, sir.
complex number system. In this complex number system, we shall discuss the in this section. We shall discuss the construction of the system of numbers and containing the familiar numbers and also predicting the solution of equations. That is, we can write here x square plus 1 is equal to 0. So this system is known as we can take that this system is known as complex numbers. This system is an complex numbers. So this is the system for you are telling in this complex analysis. So it is the complex numbers. Now we can discuss with the complex number system I am writing here in the complex number system. In the complex number system, in the C, then complex number system C are ordered pairs of real numbers. I am audible. And Vedasri?
Yes, sir. You are audible, sir.
Vedasri, వినబడుతుందా?
Yes, sir. వినిపిస్తుంది, sir.
Hello.
Hello, sir. వినిపిస్తుంది, sir.
వినబడుతుందండి? Hello. Hello.
హలో సార్. హలో హలో సార్.
సార్ కే మనది వినబడట్లేదు అనుకుంటా.
అవునవును.
Hello, sir. Hello, sir.
Hello.
Hello, sir.
Hello. I'm audible.
Yes, sir.
Hello.
హలో సార్.
I'm audible.
హలో.
Yes, sir. You are audible, sir.
వినిపిస్తుందా?
వినిపిస్తుంది, sir.
ఇయర్ ఫోన్స్ పెడతా. I am audible.
Yes, sir.
So in this system is known as the complex numbers. So we have to we have the complex system. So we have the pair numbers are into the product of the star itself. The operation of the denoted and this is addition and multiplication. We are taking this is addition and taking multiplication we are taking. So denoted by, we can write this here function as it is. We can write here A comma B plus C comma D is equal to A plus C comma B plus D. We can write this here. This is A plus C and B, A plus C and B plus D. So again we can write here. Again we can write here, and this is in the screen, A comma B. I'm doing multiplication here. A comma B into CD, AC minus BD, AD plus BC. So we can here addition and multiplication. We are A plus C and B plus D, 1 plus 1 and 2 plus 2. We are doing one element. We are multiplication A into C. I'm taking the cursor here, A into C and B minus B into D. Again we are doing A into D minus A into D minus into minus plus. So we are writing AD into BC. So in the addition and multiplication purpose we are doing here. In this addition and subtraction multiplication that appear in the right side of the definition of the familiar operation on real numbers. So in the straightforward, to check that plus and infinity, plus and multiplication defined as the both commutative and associative. Then multiplication is distributive with respect. So I'm writing here multiplicative with respect to plus. So multiplicative with respect to plus. The notation of equality. The notation of equality we are learning here. So we are learning here the notation of equality of the notation of equality of the complex numbers from quality. The notation of the equality of the complex numbers from equality in that is we can write here R into R. So defined as a both commutative and associative. So here we are writing here the notation of the quality in R and R. A comma B C comma D and equal. We can write this equal to A comma C and B is equal to B is equal to D. B is equal to D. B is equal to D. So we can here so R into R, then A is equal to C, and we can write here A is equal to C, and A is equal to C, and B is equal to D. The symbols in the following is not X plus IY. We can write here X plus IY. So we can write here X1 comma 0 and plus X2 comma 0. So we can write here X1 plus X2 comma 0 here. So therefore we can do the multiplication here. X1 comma 0 plus X2 comma 0. This is multiplication I am doing here. Then X2 comma 0 we can take here. X1 comma 0 we are multiplying here. X1 X2 comma 0. So we can define and identify the complex number X1 0 with the real number. X1 is vice versa. X1 is vice versa. We can take here the vice versa. We can take here. So that the definition we can one definition we can take here. The symbol I represents 0, 1 belongs to C. So then we can write here X plus IY. So X plus IY means X comma 0 plus 0, 1 into Y comma 0. So X comma 0 and plus 0, 1 into Y comma 0. We are doing addition. Then we are doing multiplication. So X into 0. So x comma 0 plus 0 comma y, we can write this here. So this is maybe written as x comma y. We are multiplying this one x, so this is 1 here, this is 1. So that is x comma y. So finally we can observe that, finally we observe that I square is equal to imaginary part 0 comma 1 into 0 comma 1. We can take that is minus 1 comma 0, which is identified minus 1. With identified minus 1. Why? Because I square is equal to minus 1. That is the imaginary part. So then what is I square is equal to minus 1? Then we can write I is equal to root of minus 1. So then we can take here x plus iy be used here after algebraic computation are easy. The satisfied of the normal algebra, put the rules I square is equal to minus 1. So already you can know that I square is equal to minus 1. So a plus ib, we can take an a plus ib plus c plus id, real and imaginary parts. So we can write here real parts is a plus c, and imaginary parts b plus d. So we are writing a plus i plus c plus id. A plus c means real parts. There is no imaginary parts we are taking. So that we are separating the real parts and the imaginary parts to the both sides. We can write a plus c and I into b plus c. So suppose we are multiplication this part. Here we can do that. We can write here a plus ib into c plus id. So we can write here ac minus bd. Multiplying, we are multiplying ac minus bd plus I into AD plus BC. So we are taking here also. So I into I square is equal to minus 1. So we are putting here minus 1. So I am taking the cursor here and y is equal to minus 1. So A into C, AC minus B into D, BD, I square is equal to minus 1. So AC minus BD. Again multiplying, we are taking the I common of the second part. So I into AD plus BC, we are taking, this is the real and imaginary part. So another definition we are taking here, the complex number, if the complex number x plus iy, the real number x is called the real part of x plus iy, and the real number of y is called imaginary part, real part and imaginary part of x plus iy. So here the complex number is x plus iy and real part and imaginary part. So then we are already told x is the real part and I is the imaginary part. So x is equal, we can write here. So we can write here x is equal to real part of x plus iy, and y is equal to imaginary part of x plus iy. We are taking real part and imaginary part we are taking here. So then properties, we can take that the properties here, some properties we are taking here, some properties are we are taking here. Properties of complex number. So what is associative law? So we can take the associative law, associative. So we can take the associative law here. So we can take the associative law Z1 plus Z2 plus Z3. We are taking A plus B plus C. So we can write off A plus B plus C. We have learned earlier also in the courses of the degree also A plus B plus C. We can write A plus B plus C. The first condition we are taking here. Then the second condition, existence of an additive identity. Additive identity we can take here. Additive identity we can take here. It is denoted by 0. It is denoted by, we can take here, it is denoted by 0. That is denoted by 0 means, denoted by 0 means it is 0 belongs to C. We can take that the value, we can take that here Z plus 0 and 0 plus Z is equal to Z. So why? Because In additive identity means 0. The 0 elements using here substituting z plus 0 and 0 plus z, the value is z. Then third one, we can take the third one, existence of additive inverse. Existence of additive inverse. Existence of additive inverse, we are taking existing of additive inverse. So we are taking here existing of additive inverse. So we can write here there is minus z belongs to C. So we are taking minus z in additive inverse. Why we are taking minus z? A into A inverse. So A inverse is what is that feeling? A inverse is that is an inverse function. So there is a minus z belongs to the complex number such that we can take that here z plus minus z. We can write here minus z plus z is equal to 0. So we can write in the addition property z plus minus z, the value is 0. We are taking the multiplicative additive inverse, we are taking here the value is 0. The fourth condition, commutative law for addition. Commutative law for addition. In the addition the commutative law means A plus B is equal to B plus C. The commutative, what is the commutative? A plus B is equal to B plus C. In this condition, we can write Z1 plus Z2 is equal to Z2 plus Z1 we can write here in this one. Then the fifth condition, associative law for multiplication. Associative law for multiplication. Associative law for multiplication. So we can write here Z1 into Z2 into Z3. Again, I am telling A plus B plus C, then A plus B plus C. Now here also we are writing here Z1 into Z2 into A1 into B1, A1 into B1 into C1. Now writing A1 into B1 into C1. So we are writing Z1 into Z2 into Z3. This is called associative law. Then we are going to next condition, existence of multiplicative identity. Existence of multiplicative identity is denoted by 1. Why? Because in the addition property we are denoted by 0. Z plus 0 is equal to 0 plus. But in the existence of multiplicative identity, so we can take that in the multiplication, it should be 1. So it is 1 belongs to C, we can take that here. So Z into 1 is equal to 1 into Z is equal to Z. Z into Z is equal to 1 into Z. So we go to the next condition, the seventh one. Existence of multiplicative identity. Existence of multiplicative identity, non-zero numbers. So if Z not equal to 0, so we can write here Z inverse belongs to C. So what Z inverse means already I told that addition property. So there is non-zero numbers, then only we can take that the multiplicative property, non-zero. So A into A inverse is equal to A inverse into B is equal to 1. So suppose I am writing here A into A inverse and A inverse into A. What is the value? The both should be cancelled here. So therefore the value is 1. So we can write here in the property of Z, we can write here Z into Z inverse and Z inverse into Z is equal to also. When I am taking that A here, now in the multiplication Z what we have taken here, that is Z into Z inverse. The eighth condition, commutative law. Commutative law for multiplication. Commutative law for multiplication. So that is in the addition what we are doing, A plus B is equal to B plus C. In the multiplication what we have to do, A into B is equal to B into A. So we can write here Z1 into Z2 is equal to Z2 into Z1. So then the ninth one, distributive law. Ninth one, distributive law. In the distributive law, we can write here Z1 into Z plus Z3. This is called the This is the distributive law. Z1 into A into B plus C. That means AB plus AC. We can write. So we can, in this condition, we can write here Z1 into Z2 plus Z1 into Z3. So this is the properties of the C complex numbers. So now check the some properties here. The basics of the properties we are doing here. So what is the identity? The additive identity. The additive identity, that is 0, 0. That may be written as 0 plus I0. So we can write this one 0 plus I0 is equal to plus X plus IY. X plus IY means real and imaginary part. So therefore 0 plus X, again we can write here I plus 0 plus Y. So we can write one X plus IY here. So 0 plus II, 0 plus I0 plus X plus IY, we can multiply them 0 plus X. We are taking the addition 0 plus X and I into 0 plus Y. So this is the, we are multiplying X plus IY. So we can write here X plus IY is equal to Z. So Z plus 0 is equal to also that similar one. That's the similar one. The second one, then additive inverse. The additive inverse. The additive inverse. Z is equal to X plus IY is minus X plus I minus Y. We are taking minus functions here. Additive inverse means minus. In place of positive X, we are taking minus X. In place of positive Y, we are taking negative minus Y. I plus minus X plus I, which can be written as, maybe written as minus X minus IY, or Z is equal to, we can write here minus Z. So we can not write Z, so we can write here minus Z. So in the real numbers, we can identify the two complex numbers. So we can write here two complex numbers, A plus IB, then C plus IB. So we can write here, again, we can write A plus IB. We can write as it easily, plus we can take the additive inverse C minus ID. So we can take that first one function as it easily, then we are taking the minus. So we can write A minus C plus I into B minus D. A minus C is the real part, and the B minus D is the imaginary part. So now we are going to, the another one. So then W1 minus W2 we are taking. So taking W1 minus of W2. So W1 is equal to A plus IB and W2 is equal to C plus IB. This is the part of the function. Then the multiplicative identity, we learn the multiplicative identity. Multiplicative identity. So we can take that multiplicative identity. We can take here multiplicative identity. So we can take the multiplicative identity 1, 0. We can take here 1 plus 0, 1. So then we can write here 1 into Z. 1 into Z is 1 into Z is equal, we can write here 1 plus 0, 1 into X plus IY. Earlier we are done in this theorem. So we can write here X plus IY is equal to Z. So see here, similarly we can write here Z into 1 is equal to also Z. That is Z plus 0 is equal to Z. We can write here Z plus 1 is equal to Z. So see here, then let Z naught equal to 0. Let Z naught equal to 0. Then either X naught equal to 0 or Y naught equal to 0. So therefore X square plus Y square not equal. So if X naught is equal to 0 and Y not equal to 0. So both the functions are not, X is equal to not equal to 0 and Y not equal to 0. We can write here X square plus Y square not equal to 0. So therefore we can do now the multiplicative inverse. Now the multiplicative inverse. Ardhamavutunda andi? Listening all of you?
Yes, sir.
Vedasri?
Yes, sir.
Hello? Vedasri, are you listening?
Yes, sir.
Your voice is not coming. So now the multiplicative inverse. So we can take that Z inverse is given by, now the multiplicative inverse Z inverse given by, we can write here Z inverse is equal to x by x square plus y square minus iy by x square plus y square. So we can take that is a Z inverse function. So Z into Z inverse. What is Z here? What is Z here? We are taking, what is Z here? X plus iy. So x plus iy we can take here this one x by x square plus y square minus iy by x square plus y square. So see here all of you. So x plus I, I'm taking the cursor here. This is x plus iy is the z part, and x by x square plus y square minus iy by x square plus y square. This is the z. This is the Z inverse function. So x plus iy. So now I am taking here, I am multiplying them x into x square by x square plus y square. Then immediately we can write here y into y square. Why? Because I square is equal to minus 1 minus into minus plus here. So x square into, so we can write here x square by x square, x into x square by y square. I into I square minus into minus plus y square by x square plus y square. Again, we can multiply with imaginary part also. X into y is equal to xy by x square plus y square. Then imaginary part we can take that is a already we are taking the imaginary part, so we can take that I into I. So here we can write minus of xy bar x square plus y square minus xy by x square plus y square plus xy by x square plus y square. Both are cancelled here, and also here we take and write here. We can take the LCM here, x square plus y square by x square plus y square. So this maybe it should be cancelled here. So therefore this may be cancel it plus 1 plus I0 is equal to. So why? Because 0. So xy by x square plus y square minus xy by x square plus y square, both should be cancelled here. The value is 0. So the real part is 1 and the imaginary part is 0. So similarly we can write here z inverse z is equal to 1. So this is the main one of the one. And all of you understand? అర్థమవుతుందా? అర్థమవుతుందండి?
అర్థమవుతుంది.
Yes, sir.
I'm audible?
అర్థమవుతుంది సార్.
హలో
అర్థమవుతుంది సార్.
చాట్ లో పెట్టండి, సార్ కి వినబడట్లేదు.
Then the definition that we can take that another definition. A non-empty set with two binary operations called addition and multiplication. The two binary parts, addition and multiplication, is the field of the properties. What we are dealt with the properties of C 1 to 9 additive inverse, additive law, and associative law for multiplication, existing law of identity, existing of multiplicative inverse, commutative law, and all these properties are should be satisfied. This is the one, the definition one for all the properties should be satisfied. Now I am going to some examples for your clarification. Nth roots of a complex number. I'm going to the nth roots of a complex number. Nth roots of the nth roots of the complex number. Writing a complex number in a polar form. Writing a complex number in polar form is very useful in solving an equation. Is very useful solving an equation of the form. We can write here that is z power n is equal to. The complex number already polar form, we can using the form is equal z power n is equal to a, and where we can write here where a is a given non-zero complex number, and n is a positive integer. So z power n is equal to a, we are writing here. So a is a non-zero complex number and n is a positive integer. We can take that here, n is a positive integer. So we can write here modulus of z whole power n is equal to z power n in the modulus. So it is a theta is an argument. So we can take that there is one definition here. We can take the definition. The solution of z power n is equal to a, or the solution of z power n is equal to called nth roots of a into a not equal to 0. But we can write here a is equal to rho of cos phi plus I sin phi. We can write here cos phi plus I sin phi. So we can here z is equal. So we can write here z is equal. So we can z is equal. We can write here r into cos phi cos theta plus I sin theta. So in the de Moivre's theorem, we can take that r into r cos theta plus I sin theta. So we have learned is z power n is equal to a. So we can simplify here rn is equal to cos n theta plus I sin n theta. But in the r power n, in the generally what we are doing, suppose we can do that a plus b whole square. What we can write here a plus b whole square. So we can write here a plus b whole square, generally a square plus b square plus 2ab. But it is in the general form. You can don't think it. So in that in the de Moivre's theorem, suppose 2 power n, we can write here 2n here. 2 power n times actually. So cos n theta we can write here cos n theta means cos n terms, but we can write here cos n into theta. So I'm ignoring these values. So we can write here r power n is equal cos n theta plus I sin n theta. If you take that rho of cos phi plus I sin n phi. In place of theta, I'm taking phi here. So therefore, r power n cos n theta is equal to rho cos phi. So in the cos n theta is equal to r power here I'm taking the cursor. R power n I cos theta is equal to taking rho of cos phi, and again taking r power n sin n theta is equal to rho sin Fine. The first one and the second one, here an imaginary parts we are taking here. So we can take here r power n is equal to rho and cos n theta is equal to cos phi. Therefore, r power n is equal to rho and cos n theta is equal to cos phi. So we can write here sin n theta is equal to also sin phi. So sin n is cos n theta is equal to cos phi. Then we can write sin n theta is equal to sin phi. The equation of this certification of the fulfilled. So therefore, r power n is equal to phi by n, where we can write here nth root of p denotes the positive nth root of positive real number, nth root of positive real number alpha. We can take here nth root of positive real number rho. So we can take here the z. So we can take here alpha. So we can take here z nth root of rho. We can write here cos. In the de Moivre's theorem, we can write that a by cos phi by n plus I sin phi by n a by b. We can write here. So therefore, the root of the equation Zn is equal to alpha. So this is the major the definition of this one. We can use is that. So therefore, this fact also satisfied the theta differs by an integral multiplied to alpha. So therefore, we can claim that Zn is equal to a if and only r is equal to nth root of p. So theta is equal to, we can write phi by n plus 2k phi by n. We can where k is on integer. This is the major one of the definition of this one. Suppose we can take one example, see some examples take here. Some examples we can take here. The solution of z power 4 is equal to 1 plus I are obtained the follows. As follows. Suppose we can write 1 plus I is equal to, we can take the z plus 4, 1 plus I, we can take the root 2, therefore cos pi by 4 plus I psi and pi by 4, we can take the 45, cos 45, we can take the root 2. The fourth root, we can take that here. Then we can the first fourth root, we can take that here 1 plus I is, we can take the 2 by 1 by 8 means we can take that 1 by 2 into 4, 1 by 8, therefore cos pi by 16 plus I sin pi by 16, we can take here I sin pi by 16. So 1 plus I are given by, we can take that here 2 into 1 by 8 cos pi by 16 plus ai by 12 2 plus I sin pi by 16 plus k pi by 12. So in the k, what we can write here, k is equal, we can write here for k is equal 0, 1, 2, 3 and so on. This is the major one of this one. Now we will take that some other definitions here. Definition that z is equal to x plus iy, the number. You can write here x minus iy is called conjugative. We are taking x plus iy and we are taking another one. We are taking minus one. The second one x minus iy. It is called as conjugative. Conjugated. So we can write here. So that is conjugative. Then we are. What is the conjugative of z? We can write here conjugate of z. So we can write here z bar is equal to x minus iy. So we can write here z is equal to z bar is equal to x square plus y square. We can write modulus of z square. Expression like expression line E plus IB plus C plus ID, A plus IB plus C plus ID. But we are see here C plus ID not equal to 0. So C plus ID is equal to 0. The denominator part 0, it should be infinity. So therefore A plus ID, C plus ID not equal to 0 can be simplified without resorting to polar form, and we can make the denominator with a suitable multiplication. We are taking suitable multiplication we can take in here. So now we can write here. Take here A plus IB by C plus ID. So we are taking rationalization A plus IB by C plus ID into C minus ID by C minus ID. With the denominator part, I'm rationalizing, I'm multiplying. This is C. See here, all of you. This is not C. So now I am multiplicating AC plus BD plus I into BC minus AD, real and imaginary parts. What I am taking here in the denominator part, A plus B into A minus B, A square minus B square. So we can take here C square minus D square. But I square is equal to minus 1. So minus into minus plus. So we can write here C square plus D square. So we can write here AC plus BD by C square plus D square plus I into BC minus AD by C square plus D square. So first one is the real part, and the second one is the imaginary part of that one. So we can take that some another parts also. We can take here some here we can take that one. Complex plane as a metric space definition you can write here. Complex plane as metric space. You can take here. So a definition, a metric space is a pair X comma D where X is non-empty. A metric space is a pair X comma D in the real analysis also. You can learn that X comma D is a metric space. P X comma Y and Y comma Z. We can write X comma Z here. Matrix comma X comma D, where is X is a non-empty set and D is a function, and D is a function from X into X. That's the Cartesian product of X with X into X into R in real numbers. So therefore called as distance function. Called as distance function or metric which satisfies some conditions here, or satisfies some conditions here. It satisfies some conditions here. What is the conditions in for X comma Y comma Z belongs to capital X? So first condition, what is that condition? We can take here D of X comma Y greater than or equal to 0 in a metric space. Second condition, we are take that D of X comma Y is equal to 0 if and only if X is equal to Y. Why? Because we are taking D X comma greater than Y equal to 0. X comma Y. What is X comma Y? So X is equal to 0 and Y is equal to 0. If and only the condition should be satisfied, then X is equal to 1. And third one is the symmetric. D X comma Y is equal to D Y comma X. That is symmetry. We are writing A, B, B, A. Fourth one, D X comma, already told in the definition, D X comma Y plus D Y comma Z. We can write the D X comma Z here. So D X comma Z less than or equal to D X comma Y plus D Y comma Z. This is the theorem called is triangle inequality. You can learn in the real analysis in the first year. Learned. So this is triangle inequality. So this is the theorem of concept of metric space. Then open set definition we can learn here. Open set. A subset S subset C is said to be open. Is said to be open if every Z0, if every Z0 belongs to S, I'm writing again here, Z0 belongs to S here as a corresponding real number, as a corresponding real number, epsilon greater than 0, such that n epsilon Z0 subset of S. So subset of S subset of C complex numbers is said to be open, and every Z0 is the corresponding real number epsilon should be greater than 0. So therefore n belongs to Z0 belongs to S. Then we can learn the closed set. Closed set, we can learn the definition of closed set. A subset SC is said to be closed if the complement of S in C, namely, this is S in C, namely we can write here C minus S is open. Why? Because here a set subset is said to be closed set, so it's closed. So that is a complement. S is in C means S is in the C is there. So as well as so we can write that the C minus S is an open set. Then we can take that the limit point here. Limit point. So limit point means a complex number. A complex number Z0 in C is the limit point. A complex number Z0 is a limit point of a set belongs to Z0, contains a point, contains a point of S other than Z0. See here, a complex number Z0 is the limit point. So means the Z0 is in a C is a limit point. So limit point means a set is n epsilon Z0 contains a point where it is a point of S other than Z0. So we can call it as limit point. So we can take that as some other ones also, interior points also is there. Then another one definition is here. So today, let S be a subset of C points in S which are not limit points are said to be isolated, points of S. S be a subset of C points on S. What is S? So which is the limit points already told in the limit point definition. So are said to be isolated points. This is definition. Now I am going to some problems here. Find all possible values of Z satisfying Z square is equal to minus 9, the first one condition. The second one, Z square is equal to minus K square. So we can, it is real part. We can take that. So here Z is equal to what we are writing here? Z is equal to X plus I. in the given problem, z square is equal to minus 1. So we can write here x square minus y square plus I into 2x square. So definition, the real and imaginary part separating. So we are writing here minus 1. So it should be turned. It should be done here. What is that implies? The real part, what we are writing here, x square minus y square is equal to minus 9. And the imaginary part, there is no imaginary part here. It is a zero imaginary part. So therefore, 2xy is equal to 0. So therefore, we can write here the 2xy is equal to 0. So therefore, then x is equal to 0 or y is equal to 0. Then we'll go to the another one. Then x is equal to, now y is x square minus y square is equal to minus 9. Here substituting x is equal to x square is equal to y is equal to 0. So therefore, x square is equal to minus 9, which is impossible. Why? Because this x is equal to 0 also we can substitute. Then y square is equal to also minus 9. So I am writing here the same condition here. So x is equal to 0 also, y square is equal to minus 9, which will imply that y square is equal to minus 9. So therefore we can write here y is equal to plus or minus 3. So we can write here z is equal to plus or minus 3 in this problem. This is one of the one. And now we can take that another two examples. We can take 1 minus I by 1 plus I. So we can take that this one. 1 minus I by 1 plus I. This is the 1 minus I by 1 plus I. We are taking denominator, we are taking 1 plus I, we are taking 1 minus I with the multiplication one. So we can multiply with 1 minus I and 1 minus I, 1 minus I whole square. So we can take here 1 plus I into 1 minus I. So 1 minus I whole square, 1 square, 1 minus I square plus 1 minus 2I. So we can write here, minus I square means I square means minus 1. This is minus 1 minus 1. 1 cancel here. We can write minus 2I by the denominator. We can write here 7 plus 3, 1 plus I, 1 minus I. So we can multiply a plus b, a square minus b square. So a square minus b square means I square minus 1 plus 1 is equal to 2. So we can write here minus sign. So there is a no real part is 0. And the imaginary part is minus 1. So we can take that the second one also we can take the 6 plus 3i by 7 plus 3i. And taking it the 7 minus 3i, the denominator part. 7 minus 3i, 6 plus 3i into 7 minus 3i into 7 plus 3i into 7 minus 3i. So 6 into 7, how much? 7 6 of 42 minus 6 3 18 9 plus 21i minus 9i square. But the denominator is square plus b square, 49 minus 9i square. So we can take that the real and imaginary part here. 6 into 7, 42, and 6 into 7, 3i now. So we can take here, we can take that here. I square means minus 1, I square means minus 1, minus into minus. This one is minus into minus plus. So we can write here 42 plus 9, 51. 42. That means just a minute, 6 into 7, 42. 6 into 3 into 6 into 3, 89. 3 into 7, 21. Minus 3 into 3, minus 9. I into I square minus 1, minus into minus 42 plus 9, 51. We can write here 51 minus plus 51 plus, we can write here 21 minus 18. So 3i by 49 minus I square means minus into minus plus is 9 is equal to 51 plus 3i by 49 58 we can take here. So we can take here 11 is coming 11. 49 plus 9 I am correct. This 45 is how should come? 6 7 42. 6 3 is 18. 3 7 is 21. 3 3 is 9. 42 9 51. It is a printing mistake. So here we can write 51 by 58. Okay, we can write there this one and this one I will written as this one. So this is the, we are taking that one. This is the, any dots? Any dots? Any dots? Vedasri, Srilata, Dhanalakshmi. Am audible? So this one on the first one. Next, we will go to the some properties. Prove the triangle inequality, very important theorem. Prove the triangle inequality. Prove the triangle inequality. So we can take that z plus w is modulus of w for any z comma w belongs to C. So then first condition, the first one, the second one, modulus of z minus modulus of w less than or equal to modulus of z minus w for any z comma w belongs to C. So first we can do first one, we can do the solution. Z plus w by z bar plus w. You can multiply them z into z bar. Then we can multiply w into w bar. And again z into w bar plus z bar w. So we are multiplying everyone, z into z bar, z into w bar, w into z bar, w into z bar, and w into w bar. So I am written here that one w. So w into w bar I am written here. Then z into w bar. W into z bar. So I am written here that one. So here we can write here modulus of z square. Then w bar we can write here modulus of w whole square. Then 2 into real part we can take here 2 into real part z2 zw. Why? Because see here I am underlining z bar w z. So we can 2 into real part, that is the real part zw bar. There we can, so we can write here less than or equal to modulus of z whole square, then w whole square, then 2 into z w. So we can write here is equal to modulus of z square, modulus of w square, 2 modulus of zw. We can write here. So this is a square plus b square plus 2ab may be written as modulus of z plus modulus of w. This is whole square, a plus b whole square formula. So we can write here. So also we can write this one. Also this may be written as z plus w, z bar plus w bar is equal to z plus w and z plus w bar. It may be also may be written as z plus w less than or equal to, we can write here z plus w. This is the one of theorem. I'm taking the graph of this one. It's not coming, I'm giving you. Now profit not coming. This is good. Exactly that. So we can take that this one W. This is Z plus W. This is AZ. This is complex number C Z plus W. Then 0. Then X. So this is the first one of the parallelogram now. Then we can take the second one here. Modulus of Z. So modulus of Z we can write here. W plus Z minus W. Less than or equal to, so the formula right here, W plus modulus of Z plus Z minus W. Using this first equation, first one. So we can write here modulus of Z minus W, that will be written as Z minus W. Interchanging, we are taking the interchanging of the interchanging Z and W. So we can write here modulus of W minus Z. We can write here modulus of W minus Z. We can write here Z minus W. W minus Z, Z minus W. We can write here. So we can write here this one, changing the interchanging that one. We can write here modulus of Z1 is equal to modulus of Z minus 1 for any Z1 belongs to C. So we can write here Z minus W. We can write here less than or equal to Z minus W. This is the result of the equivalent of the state. This is the result of the equivalent to the statement of the side of the triangle length greater than to equal to the lengths of the other two sides also. We can learn this parallelogram now. So in this unit we can learn that in the summary in this unit we can that's A plus B and C plus B. So many learn that in the relations of the part. Any more doubts? Any more doubts? Am I audible?
Yes, sir.
I am audible?
Yes, sir.
Yes, tell me Vedasri. Tell me. I am audible? Hello?
Yes,
audible?
sir. Audible, sir.
వినపడుతుందా? Hello? So Z minus W.
వినబడుతుంది, sir.
Yeah. So this is the one, another one. Show that the equation, another problem we can leave here. So that the equation of the circle in the complex plane can be put in the form of, so we can write here Z into Z bar, dz bar plus b bar Z plus C is equal to 0. So we can take one triangle here, one circle we can take here. This is a complex A. If we put P of Z, so we can take let the complex. Let the complex number A power A and A represent the A power number A, we can take A represents the center, represent the center of the given circle, and R. So if the complex number given in the A is the center of the circle, and what is the radius? R is the given with the radius of the circle, or with the radius of the circle. Then we can do the let P of Z. Let P of Z be any point on the circle. So Z minus A is equal to, so we can take that Z minus A is equal to R. So we can, suppose we can take that Z minus A whole square is equal to R square. So we can get it here, Z minus A under root of, Z minus A into Z minus A. This is a bar. So we can write here, this is also R square. Z minus A, within the bracket Z bar, A minus bar. So this is also, we can take that R square. So therefore, Z into Z bar minus A bar Z minus A Z bar plus A bar minus R square is equal to 0. We can take here B is equal to minus A and C is equal to A bar minus R square. We can write here. So we can write here modulus of A square minus modulus of A square minus R square. So we can write here again here Z bar BZ bar B bar Z plus C is equal to 0, which represents the equation is a circle. Why? Because Z minus A is equal to, we can write here Z modulus of Z minus A whole square is equal to R square. We can write here Z minus A in the bracket Z bar minus A bar. So Z bar minus AZ bar minus AZ bar plus A minus R square is equal to 0. So therefore, Z bar plus BZ bar plus B bar Z plus C is equal to 0. We can write here this one will be taken here. So then describe the values also. We can take that some another one. Describe the values, the set of values for which Z minus 3 by Z plus 3 is equal to, we can take here Z minus 3 by Z plus 3. First one we can take that Z minus 3. So we can write that Z minus 3 is equal to 2 into, we are taking the denominator right side, 2 into Z plus 3, the one. So this is a moderate, this is the modulus, 2 into Z. Suppose we are taking X plus I by real and imaginary part. So we can take then Z minus 3, we can write here the X minus 3 whole square plus Y square. So means that is our real part is X minus 3 in place of X, that is the Z minus 3, writing X minus 3 whole square. So we can, and we can write here, we can write here and Z plus 3. We can write here Z plus 3. So and we can take here also here X plus 3 whole square plus there is no imaginary part. So we can write here so that Z minus 3 is equal to 2 into modulus of Z plus 3. So we can here, just a minute. So we can here Z minus 3 is equal to 2 into Z plus 3 X square plus Y square. So Z minus 3 into Z plus 3, that is X square plus Y square. So we can write here what is that one here, what we can write here X minus I by, there is only real part, there is no imaginary part. Z of Z plus 2 into Z modulus of Z plus 3, that we can write as X square plus Y square. So we can multiply. So we can write here X square. This one, first one, we can minus whole square, X square plus Y square plus 10x plus 9. X square plus Y square plus 10x plus 9. So the first one is 10x plus 9. We can 10x plus 9. So we can write here x plus 5 whole square plus Y square is equal to 16. So we can take the 25 minus 9 is equal to 16. So therefore we can take that x plus 5 whole square plus Y square is equal to 16. So we can take that modulus of Z plus 5 is equal to under root of 16 is equal to. Why we are taking 25 here? So 16, 25 taking 25 minus 9 is equal to 16. So that's why we can write that Z plus 5 is equal for a circle of the radius The center is minus 5, 0. So hence the points. Next time the circle z plus 5 is equal to. So hence the circle z plus 5 is equal to 4. Next one will go to the next one. So hence this the points, then the point is, hence the point is we can write here, hence the point, hence the point, hence the point satisfying the circle z plus 5 is equal to 4. So we can write here the distance of a point Pz, the distance of a point Pz from the point B3 is a twice distance, is a twice a twice distance P from the point A minus 3. Then P lies on the circle modulus of z plus 5 is equal to 4, the center of point. The center of point C minus 5. Yes. Already we have found the concurrent radius is minus 2. Sorry. So we can take the diagram here. See here, this is the diagram what here the set of satisfying. So here is the, I'm taking the cursor Pz is the point of B3. Here we are taking here point, we are taking this is the point to this is the point. Pz to B3 we are taking, and the distance between Pz is minus 3. So between the distance is the minus 3, and the lies z plus 5 is equal to 4. For the center C is equal to minus 5. So and radius the C is minus 5 and the radius is 4. So that is the then this 4 we can written here. So any points of the satisfied the circle the equality is 1. So any points of the circle the 1 here we can write the given inequality. The given inequality is equivalent to the given inequality is equivalent to, we are already learned z minus 3 2 of z plus 3 r under root of x plus 3 sorry x minus 3 whole square plus y square less than 2 under root of x plus 3 plus y square. Already we learned that one x minus 3 x minus 3 plus y, this one we can take it squaring and simplifying. The squaring and simplifying this becomes already well x square plus y square 10x plus 9 greater than 0. We can write here x square x plus 5 whole square plus y square greater than 16. So therefore we can write here. So we can write here z plus 5 greater than 4. So we can write here z plus 5. So they greater than 4. This is the one, the first and second one of the that one. Then we can learn another one. Another one. for each of the following points on C, the corresponding points of the unit sphere. Yes. First one, 0. For each of the following point of the C, given a corresponding point of the sphere. Yes. So suppose we are taking the sphere, suppose x is equal to 0, we can take here, suppose x is equal to 0 and y is equal to 0. So x is equal to 0 and y is equal to 0, we can take that z is equal to -1. And we can take that z then I1 plus II we can take in here. So x is equal to 1 and the y is equal to 1 in equation earlier taken. So x is equal to from the equation already taken from the equation we have 3 taken that earlier. So we can take that x is equal to 2 by 3 and y is equal to 2 by 3 and also z is equal to also 2 by 3. But it is but here x is equal to 0 and y is equal to 0 and then z is equal to -1. So this is the therefore another one. You can take that the third condition. The points of the corresponding in the same way, x is equal to 3 and y is equal to 2. Third one 3 plus 2y, x is equal to 3 and y is equal to, it's a real and imaginary point. So x is equal to 3 by 7 and y is equal to 2 by 7. So z is equal to also, we can learn that 6 by 7. From 1 to 3 the sphere respectively, we can take that 0, 0, -1 and 2 by 3, 2 by 3, -1 and 3 by 7, 2 by 7 and 6 by 7. You can take that this one here. Next one, the one problem we can learn here. Should come the problem. Solve the equation. Solve the equation. Z power 4, 4iz square plus is equal 4iz square plus 8 is equal to 0. So we can put here z, we can put w is equal to z square. So we can put the equation. The equation becomes here w square plus 4iw. We are substituting z square, w is equal to z square. So we can write here w square plus 4iw plus 8 is equal to 0. So, but in the quadratic form, the variable namely is equal to az square plus bz plus c is equal to 0, but a not equal to 0. So we can write here. So what is the formula? Minus b plus r minus b square minus b plus r minus the root of b square minus 4ac by minus b plus r minus b square minus 4ac by 2. So we can take this one. So we can write
ఏమైంది పోయింది ఇప్పుడు అడిగి నువ్వు హలో సార్
వేదశ్రీ డిలీట్ హలో శ్రీలత శ్రీలత హలో శ్రీలత గారా?
హలో అవునండి.
మీరు అసైన్మెంట్స్ రాసిరా?
రాస్తున్నాను మేడం. మీరెవరు?
నేను